Okay, let's continue in section 4.1. We're talking about inverse functions. In the first video, we found the inverse of a linear function. And now let's try to find the inverse for this quadratic y equals x squared. So last time we learned three different ways to find the inverse. We could do it with a table or a graph or symbolically. Let's start with the graph. So I have the graph of y equals x squared drawn, and I also drew the line y equals x. Remember that the inverse function is just going to be a reflection over the line y equals x. So that's important to remember. The other thing to remember is that to get points on the new graph, all we have to do is switch x and y from the old graph. So let's look at this point right here at 2, 4. What are the new coordinates? 4, 2. And look at this point at 1, 1. What are the new coordinates? 1, 1. 0, 0 stays at 0, 0. And then negative 1, 1 becomes 1, negative 1. So it's down here. And negative 2, 4 becomes 4, negative 2. So it's over here. And so we can draw the curve through these points. And there's a problem with that. So, you know, if we have f of x equals x squared here in blue, then this graph in green is supposed to be f inverse of x. But can you see what's wrong? The inverse function is supposed to be a function, and this graph is not a function. You can see that it fails the vertical line test. So we have to write no, because it's not a function. And so let's see here. Could we look at f of x equals x squared, and could we predict that we were going to have this problem before we go ahead and sketch the graph? That's what I'd like to talk about right now. So what we're saying here is that f inverse of x must be a function. And what exactly does that mean? That means for each input, there is exactly one output. And so what does that tell us about f of x? That tells us that f of x must have the following property. Remember, the relationship between f and f inverse is we switch x and y, or we switch the input and the output. So in order for f inverse to have each to satisfy this condition, to say for each input there's exactly one output, then for f of x, we've got to make an equivalent condition by switching the words input and output. F of x must satisfy the following condition for each output. There is exactly one input. So when f, and this has a name. For each output, there's exactly one input. That's the definition of something called one-to-one. So we say the function is one-to-one if for each output there's exactly one input. And so f of x must be one-to-one in order to have an inverse. Or another way to say that is to say that f of x must be one-to-one to be invertible. Okay, so the same way that the inverse function has to pass a vertical line test, well, we can think of switching x and y in that sense also. For f inverse to pass a vertical line test, f of x must pass a horizontal line test. For f inverse to pass the vertical line test, to be a function, f must pass the horizontal line test. To be one-to-one. Okay, so when we draw a horizontal line across f of x, we see that it hits the graph more than once, and so we say that it's not one-to-one, and so it's not invertible. Or another way to say that is to say that the output 4 has more than one input, has an input -2 and another input 2. F of x is still a function, it's just not invertible. And so we have this typed up as well. So a function is a relation so that for each input there's exactly one output, and a function is one-to-one if for each output there's exactly one input. So a function must be one-to-one for it to be invertible. If the function is not one-to-one, then its graph does not pass the horizontal line test. So the big question then is, what are we going to do in order to get an inverse function for y equals x squared? Now, and you should know already what the inverse is. What's the opposite of squaring a number? Well, it's the square root. It's the square root. So what we're trying to do is get to the square root function. Now, of course, the green graph doesn't look like the square root function, but it will in just a moment when we just make one little modification. So actually, let's come down here to the bottom. So what can we do? What can we do to define an inverse for y equals x squared? And the answer is restrict the domain. And so what that means is that we can't find an inverse for the entire function y equals x squared, so we're going to have to do the next best thing. We're going to find an inverse for as much of it as we can. And so we're going to come back up here. Maybe the graph is the nicest place to see this restriction. What we're going to do is we're going to erase, or we're going to get rid of as much of this graph as we need to in order to make it one-to-one. And so if we just take the left half of the parabola and get rid of it, then the right half of the parabola is one-to-one. Right now it passes the horizontal line test. So this is a nice graph, and let's just label it a little bit better here. So let's label this graph in blue. This is f of x equals x squared, where x is greater or equal to 0. And so then what's the consequence for the inverse? Well, then we get rid of the bottom half of f inverse, and now what we have is a real function. It is a function. And so now we can come back and we can say, yes, this is f inverse, right? And in fact, this is a familiar function. F inverse of x is equal to the square root of x. And that's a graph that we know, that we've seen before.